Hello, welcome to the course on power electronics with wide bandgap devices. In the last class, I have started discussion about the crosstalk related consideration. So how the problem during the turn on and turn off time of the switch is happening and how we can mitigate them. So in the last lecture, I have discussed mostly about the passive type of consideration. So what kind of solution exists if we use the passive components, and also I have started discussion about the active related solutions. So as you have seen in the passive related solutions, we can either connect capacitance or the voltage, negative voltage we can supply. So basically there are two different mechanism. First is that we can provide impedance. Requirement of the input impedance depends on the capacitance that we can connect, and the second is that how we can change the voltage level so that it can provide the required path. So this type of solutions mainly we have focused. Now in passive solutions, this kind of component, they are fixed in nature. Means if the voltage or anything vary with respect to the load condition, input condition or the output condition, then we cannot change all this parameter. So that is why we started looking for a solution which can provide required voltage or the impedance level based on the output characteristics or the change in the load, and also it can provide us a solution so where we can actually control all the parameters. Okay, so that is where the active component comes into picture. So let's see how this is working. So as I have told in the last class, so there are like different types of like a problem which can affect the switching characteristics. So the problem can come from gate drive, parasitics, crosstalk, and additional element. So they may not create that much problem, but those can also be part of this switching characteristics effect. So they are phase lag, heat sink, and motor or cable load. Okay, so now we are discussing about this crosstalk. So let's see the active solution which are existing in nature or which can be a possible solution for wide bandgap devices for this crosstalk mitigation. So you have already seen this kind of diagram in the last class. So the circuit which I am showing you, so I am considering the same network. So one of the legs of the three phases. So let's say this is phase A. So where two switches are connected. So one upper switch and another is lower switch, right? So now upper switch and lower switch, if they are connected in series, so we have to consider that both are not in turn on condition at the same time. Okay, so for that we have to provide a sufficient dead gap so that one switch when it turns off, then the other switch will turn on. So those things are taken care of. Now when one switch is turning off or other switch is turning on, so during that time the transient due to turn on and turn off can affect the switch which may not be in the working condition or the complementary switch. Okay, so now you have seen that like one solution I have already provided. So there the capacitance was connected, right? So now here all the components remain same, means this RGH, so RGH, RGL, they are the external gate resistances. So as you can see from this, so this RGL and RGH, so they are external gate resistance. They are connected to the gate drive circuit, external resistance. Right. Now the capacitance which we are using for this active solution, so that they are given as CAH and CAL. So they are, let's say, auxiliary capacitance. They are helping for this crosstalk mitigation. Now these capacitances you have already seen in the passive kind of solution. we are also using this here, but the difference is that we are using two different switches, means like with respect to each capacitance there one switch is connected in series with this. As you can see, for the upper switch it is SAH, for lower switch it is SAL. So these two switches SAH and SAL, these are also, you can call it as auxiliary switches. So these switches helps this capacitor to charge with respect to different voltage level, or it can actually charge in the different polarity. So basically what is happening, so when we are connecting these switches, based on the switching turn on and turn off condition, we can actually regulate this impedance. So that is why this kind of technique which I am discussing in this particular slide, this is known as gate impedance regulation. So you can refer this as GIR or gate impedance regulation, right? So the idea is that we can regulate the impedance here by using the switches. So the switch which coming into picture are SAH and SAL. Now you can see these switches are connected to the capacitance, but there are other switches which are connected to the gate driver network. So you can see, so there are like two switches with respect to upper network, so that is S1H and S2H, and two switches with respect to the lower network, S1H and S1L and S2L. So these two switches are connected to the gate driver network and it is having two different voltages. So one is the positive voltage for upper switch, let's say S1H, and another is the negative voltage S2H. So here we have two different potential voltages. So V1H and V1L, they are positive voltages, right? And then similarly V2H and V2L, they are negative voltages. So in this particular solution, two different potential voltages are used. Okay. Now these switches, you can see the normal switches S1H, S2H, S1L and S2L. So they are basically gate driver switches connected to the gate driver network. So this switches, so you can see here S1H, S2H, then S1L, then S2L. So now these switches are connected to the gate driver network in order to provide charging of the capacitor and charging of the input capacitor of the switch. So there are two different capacitor, auxiliary capacitor and the input capacitance of the switch. So in different time we may need different switches to charge with respect to required capacitances. Means if the switch is on, so then if we have to provide positive voltage, then S1H or S1L switches will be on, and then the positive voltage will find the path with respect to that particular switch, let's say S1H, then external resistance RGH and internal resistance RG in, and then through the input capacitance of the gate, and that is how the switch will turn on, right? And then in that time what will happen, the capacitance which is connected in the path where basically we are providing turn on and turn off transient path, so that is auxiliary capacitance SAH or the SAL, any of the capacitances if you see, so they are connected in series with the switch, auxiliary switch, and that is actually helping during the turn on time the total capacitance or the net capacitance in that path, that will be negligible. Means if we connect only capacitance, then whatever capacitance will come, let's say 1 microfarad, so that capacitance will add up with the gate capacitance, and that will increase the net capacitance at the input of the switch, and that may affect turn on and turn off duration. But if we are connecting this capacitance in series with any switch or the diode, then what will happen? The parasitic capacitance of the switch or the diode will be very less. So it will be in the picofarad range. So the net capacitance in that part will be in picofarad or less than that. So that anyway will not affect the gate input impedance. So that is why this path, like for active solution, is not creating any problem during the turn on condition. Okay. So generally this I have already discussed in the passive solution, where this capacitance, if we connect, although we may have the solution for the problem of high current or the turn off during turn off duration, this can find the path through the capacitance, but it can increase the turn on and turn off duration. But here this problem will not come. Okay. So let's see how the working principle is. So I have divided it in different times. So you can see here. So this is, let's say, for there are different sub interval for this active operation. So let's consider the first sub interval. So sub interval here it is given as T0 to T1. So what is happening in this T0 to T1 duration? So basically, excuse me. So in this duration, so the current will, so basically this V2H or the V2L, it will charge the auxiliary capacitances. And what will be the charging path? So the charging path will be like this. So you can see here, so this auxiliary capacitances CAH and CAL are pre-charged through body diodes of the switches. Body diodes. So this body diodes, body SAH and SAL. Okay. So these capacitances are pre-charged. Now you can see from the direction of the current, this pre-charge voltage will be negative. Means it is charging from V2H, and through this body diode of the SAH and the internal resistance, and then switch S2H. So this is the loop which is helping to charge this capacitance. Okay. So then you can actually also write down the voltage across both the capacitances CAH and CAL will be negative, and it will complete the pre-charging at the end of this particular subinterval. Okay. So now this is with respect to the main function of this particular subinterval, to charge these capacitances. Now if we consider subinterval 2, then in the subinterval 2 what is happening? So basically this is for T1 to T2 duration. So you can see here, so this is given here. So here in this particular duration, so what is happening? Initialization is complete. So now the lower switch, we are considering lower switch, turning on of the lower switch. Lower switch at the end of this particular subinterval means at T2, the lower switch starts to turn on. Okay, so now this switch will be turning on at the end of subinterval. So we have given this particular subinterval, it actually completes this initialization. So like in the first subinterval, so their initialization started and it should complete by this subinterval. Okay. Now next is that, so here the lower switch is turning on. So this turning on signal provided here. So you can see here, this is the signal which is given to the gate of the lower switch. So this particular signal you can actually see here. Okay. Now upper switch is not on in this condition. Now what will happen? In this case, lower switch now this lower switch, how it will be turning on? As I told you earlier, so basically the current from V1L, so this current from, let's say, V1L, it will flow through this S1L through the gate resistance and the internal resistance of the switch. Yes, so the current path you can see here for the lower switch in this case, and in this case what will happen, as the switch is turning on, the same turn on transient will affect the upper switch. So then what will happen, due to the voltage, high voltage in the upper switch, or whatever voltage will come across the upper switch, that will cause current to flow through the Miller capacitance of the upper switch. So what is the current path? So basically the current path, as you know, so this generally flows through the Miller capacitance. So let me just use the thicker line so that it will be highlighted properly. So this, through this capacitance, then it will find the path through this internal resistance of the switch, and then through this capacitance AH, so the auxiliary capacitance, it will flow. Okay. Now this auxiliary capacitance, as you can see here, so in this case this auxiliary capacitance, it will provide the low impedance path, and the current will flow through the auxiliary capacitance to the device, and then it will not, because you know it is not flowing through the gate driver part, so that is why it will not turn on the upper switch. So upper switch is protected during this crosstalk turn on condition. Now the lower switch, if you see here, so this is with respect to the upper switch. Now the lower switch current path already I have shown. I hope it is visible to you. So this is the current path. So I am just highlighting it again using the thicker line. So this is the current path for the lower switch. Now you can see this CGSL. So basically this CGS, so this is connected across this CAL and the switch. But as I told you earlier, this particular branch will have net capacitance in picofarad. So this particular branch is in picofarad, right? It will be much smaller. So this CGSL here, it will be much larger than that of the net capacitance coming CAL that will be coming in parallel with the either switch or the diode capacitance, and that will be very small. So that will be coming in parallel with the, so it will be having capacitance of CGSAL. So that is why this CGSL will be much higher. So this line will not impact the turn on condition. So the turn on condition, then in this case crosstalk is eliminated. So the net, so basically the main outcome from this particular subinterval is that crosstalk of turn on is suppressed. So basically there are two problem comes during the turn on condition. First is that the upper switch can turn on if we don't have the protection can be anything that can. So here we are using the impedance kind of protection. So but we are regulating the impedance. So now this and another thing is that it can increase the turn on time. So turn on time we are not increasing by considering that switch capacitance, which will be much lesser value, the net effect will be less, and also we are providing the capacitance path which is helping the upper switch to remain in the off condition during the turn on of the lower switch. So this is the conclusion of this particular subinterval. Now next move to the subinterval T3 to T4. So now this switch is on. So basically lower switch, the on condition we have seen. So now let's consider what happens in the turn off condition. So during turn off condition, so what we have to consider here is that, so basically this capacitance, so you have seen here the previously this capacitance initially it was charged to the negative voltage, but now the current was flowing in this particular subinterval, the previous subinterval, in the positive direction. So the net effect will cancel each other. So basically whatever voltage, negative voltage was there in the capacitance, it will cancel out with respect to the positive charge in the capacitance. Now what we have to do in this particular subinterval, we have to charge this capacitance again. So basically this particular subinterval, it is helping the capacitance to charge. It is same as the previous step where we have actually used this particular loop for charging. Okay, so now same loop we are using for charging. Okay, now here another thing is that in this case the current is flowing through the gate capacitance also. So the gate capacitance, it is also charging in the negative polarity. Okay. So this step here, the all the switching condition it remains. This step is same as the previous subintervals. Remain same. So this is for same for the lower switch as previous subinterval was subinterval 3. Here it is subinterval 4 as subinterval 3. Okay. Now, so this negative power supply as I have shown in the upper switch. So the negative, the supply V2H, which is basically negative supply here. So as you have seen in the previous case, so there was some positive voltage will be appearing across CAH and CGSH. Although we have precharged this capacitance to negative value. So due to this current, because we are considering this current may be very high due to CDVDT, this CGDH it will be very low, and this DVDT it will be very high, because this is turning off, so the voltage should go from 0 to VDS. VDS, if it is let's say 1000 volts, so then this current will be very high, and it may cause the voltage across these two capacitances, this CAH and CGSH, to become positive. Means like, although it will balance out the negative voltage which was there in the capacitance, and still there will be some voltage which will be appearing across the capacitance, so it will cause positive voltage to appear across this capacitance. Now what we have seen in the subinterval 1, we have pre-charged this auxiliary capacitance to negative voltage. Now in this particular step, what is happening? So this V2H is helping this CAH auxiliary capacitance to go back to pre-charged value. So one thing is that if it is having 0 voltage, then immediately it will charge to pre-charged value, which will be equal to V2H. So basically in normal condition, this VCAH should be equal to V2H. Now because the current in this particular capacitance was in the opposite direction, so the voltage will be less than V2H. It can be either 0 or positive, any value. So in this step, what is happening? Lower switch will be operating as the same condition in subinterval 3, but this upper switch capacitance, it will go back to the pre-charged condition. And similarly the gate capacitance CGSH, it will also have some voltage due to the current flowing through it, so it will also go back to the previous condition, so that it will be ready for the next cycle. Okay, so that is why in this particular step the switch S2H is on, and through this internal resistance, either these capacitances are discharging or it is probably the auxiliary capacitor is charging. Okay, so this is the thing is happening in this particular subinterval. Now at the end of this particular subinterval, means at T4, the lower switch starts to turn off. So turn on transient, you have seen how it is mitigated. Now we will see what is happening during the turn off condition. So basically turn off So how it is happening? So when this lower switch is turning off, as you can see the signal which is given here. So this is now, it is in off, it is going to the off from on. So then in this case, in the upper switch, SAH will be in on condition. Okay. Now SAH is on, then how the current will flow? So as you have seen, if the device turns off, the negative voltage generally appears across the upper switch, right? So the problem was that if the negative voltage go beyond the negative voltage rating of the upper switch, then it will destroy the device and the reliability. So that is why in this case, what is happening? The turn off path is provided through these capacitances, and the capacitance current path will be equal to this. So you can see here, so there is a current path through this switch and the capacitance, and then it will go also through the capacitances here. Okay, so now this capacitance polarity is negative, and then basically the current SH is on, so the current it is flowing through this capacitance in this particular direction. So due to this, what is happening? So basically so that is why, so this particular path current direction will be restricted. So the current in the gate driver, so basically C to H will not be impacted. So only the low impedance path, through the low impedance path the current will flow, and then it will not affect the lower voltage level of the upper switch. So then it will also be protected during the turn off condition. So at the end of this subinterval, turn off okay. Now turn off of the switches complete in this particular subinterval. So now next is that turn off part is done. Now what we have to do? We have to make sure that all the condition remain same as the first subinterval, so that the switch will be ready again to turn on. So you can see here. So basically in this particular subinterval, full turn off of lower switch completes. SAH is off and CAH is disconnected. Okay, now C2H starts, not C2, CAH starts to charge So in this case, what is happening? The current is flowing through, so basically this S2H RGH through this to the gate capacitance. So basically CGSH will be charged from this switch, so body diode, and then V2H or let me just write down that CGSH discharges. So then it will be discharges through this internal resistance RGH. So you can see, so basically what happened in the previous step, so this capacitance was charged in the opposite direction, means the voltage across this gate capacitance of the upper switch, it was negative, right? So basically you can see here with respect to this capacitance current, the voltage polarity will be negative. Now this capacitance should discharge in order to make this circuit equivalent to the subinterval 1. So in the subinterval 1, what was the case? In the subinterval 1, so this capacitance voltage was 0, means like this capacitor was in uncharged condition. So only auxiliary capacitances were in the pre-charged condition. Now due to turn off, some current was flowing through this capacitance, gate capacitance of the upper switch. Now we have to make sure that this capacitance is completely in the previous condition, or the capacitance voltage or the charge in the capacitance will become 0 at the end of the complete interval. So this is what is happening in this subinterval 6. So at the end of this subinterval, so this gate impedance regulation based crosstalk mitigation completes. So we can, as you can see, we can regulate the impedance based on our requirement or based on the turn on and turn off transient in this particular method. So this method is very useful, and also it provides active kind of solution. So now another method with respect to this active solution is gate voltage control, or the GVC. So I'll be discussing about that GVC in the next lecture. Thank you.